Assalamu alaikum, dear students. In our today's lecture, we will focus on two topics. One is the integral representation of the Bessel's function. So you must turn to page 578 of the book by Orthogonal, and you must also consult my notes here, few pages of my notes. Now these are the pages which I have already sent to you. So these two references must be before you when you are attending this lecture. Okay, so the integral representation of the Bessel's function is given by this expression, this one, Jnx is equal to 1 over pi 0 to pi cos n theta minus x sine theta d theta. We will prove this expression. In fact, we will derive this integral representation, and here is the derivation. We will take t is equal to e to the power I theta in our generating function of the Bessel's function. So when we substitute t is equal to e to the power I theta in the generating function, we get this equation: e to the power x over 2 e to the power I theta minus e to the power minus I theta. And if you expand these two exponential and subtract them, you will get e to the power x over 2 sine theta, which is equal to e to the power ix sine theta. Now this exponential has both the real and imaginary parts, and similarly on the right hand side of the generating function, where you have summation n from minus infinity to plus infinity, Jnx into t to the power n. So that is the right hand side of the generating function, and when we substitute t is equal to e to the power I theta in the right hand side, we get this equation: j naught x plus 2 into j2x cos 2 theta plus j4x cos 4 theta, etc., plus 2 iota j1x sine theta plus j3x sine 3 theta, and so on. So what I have done here is the series from n is equal to minus infinity to plus infinity. I have taken j naught x, separated j naught x, and then paired up the odd index Bessel's function with of negative integers with the odd index Bessel functions with the positive integers, to get this term 2 iota j1x sine theta plus j3x sine 3 theta. Similarly, the even indexed negative Bessel's function and the positively indexed even Bessel functions have been grouped to get the second term, and this is being explained over here. If you write j1x e to the power I theta, that is the term corresponding to n is equal to 1, and if you pair it with the term corresponding to n is equal to minus 1, you get j minus 1 x e to the power minus I theta, and this is equal to j1x e to the power I theta minus e to the power minus I theta, because j minus 1x is equal to minus j1x, which is the parity property of Bessel's function. So we have grouped these two terms, j1 and j minus 1, to get 2 iota j1x sine theta. Similarly, if we group the even term, even indexed positive terms with the even indexed negative terms, for example j2x e to the power 2i theta plus j minus 2x e to the power minus 2i theta, we get 2j2x cos 2 theta, because j minus 2x is equal to j2x, again the parity property. So this is how we have grouped the even indexed Bessel's functions in this term and the odd indexed Bessel function in this term. So now if we compare the real part of the right hand side, because this equation, this e to the power ix theta is obviously cos x sine theta plus iota sine x sine theta. So the real part of this left hand side is cos x sine theta, and the real part on the right hand side is j naught x plus this term. So this is, I have written here, cos x sine theta is equal to j naught x 2n is equal to infinity 1 to infinity j2nx cos 2n theta, and similarly comparing the imaginary parts, this is what we get. Now we will use the orthogonal property of the cosine and sine functions here. This is the orthogonal property for the cosine function, and this is the orthogonal property for the sine function. So before we use these properties, what we will do, we will multiply this equation with cos theta, cos n theta, and integrate from 0 to pi, and we will multiply this equation with sine n theta and integrate from 0 to pi, and what we get is let me show you the next page. Yeah, this is what we have done here. We have okay, so we have multiplied the first equation by of a above by cos m theta and integrate, and we multiply the second equation. We will do it later. So multiplying the first equation by cos m theta and integrating from 0 to pi, we get this thing, and similarly we multiply the right hand side with cos m theta and integrate, so we get this equation, j naught x 0 to pi cos m theta d theta plus 2 sigma j 2nx into cos m theta cos 2n theta into cos m theta and integrate. So here we will use the orthogonal property of cos theta, because cos 2n theta into cos n m theta from integral from 0 to pi will give us this term 2n is equal to 1 to infinity j2n theta into pi over 2. So this is the step where we have used the orthogonal property of the cosine function. As long as j naught x is concerned, when we multiply this, and this integral is 0, so this is what we get as a result of this step, and this is further equal to, as you see, this integral is using the orthogonal property is equal to jnx when n is even and is equal to 0 when n is odd. Similarly, we multiply the second equation by sine m theta and integrate, and we get this equation, that 1 over pi 0 to pi is equal to, this integral is equal to 0 when n is even, and when is equal to odd when n is odd. So if we add up these two terms, I have what I've done. Okay, so when we combine these two, we get the integral representation as shown here. That adding these two results, we will get Jnx is equal to 1 over pi 0 to pi, and this is what we get by adding. And when we look at this integrand, we see that this is cos n theta minus x sine theta into d theta. So this is how we establish the integral representation of the Bessel's function. And as a special case, if you put n is equal to 0, we will get j naught x into is equal to 1 over pi 0 to pi cos x sine theta d theta. Right, so this integral representation is very useful in calculating integrals of this type, because by conventional techniques this integration is not very simple, but using the integral representation of Bessel's function, we can calculate such integrals very easily, because if say you have cos 2 theta minus x sine theta d theta, so this integral will be equal to j2x, and so on. Right, so let us now apply this integral representation to a very basic physical problems. As example 5.14, this is Fraunhofer diffraction through circular aperture. So when here we have a circular aperture, this one, and we have an incident beam which is diffracted through an angle alpha, and the parameters shown here, we get the amplitude of this Fraunhofer diffraction given by this expression, that phi is integral from 0 to a, and another integral from 0 to pi of this term e to the power I b r sine theta d theta r dr, where b is given by 2 pi over lambda into sine alpha. So you must note the parameters being used here. Phi is the amplitude of the diffracted beam, theta is the azimuth angle in the plane of the circular aperture, alpha a is the radius of this aperture, and b is equal to this. So let us now calculate phi and find the intensity of the diffracted beam. So this integral, let us take up this integral first, that is the integral from 0 to 2 pi e to the power I b r sine theta into d theta. So we can write this integral as shown here. E to the power I b r sine theta is equal to cos b r sine theta d theta plus iota sine b r sine theta d theta, and this integral is splitted into two parts. First part from 0 to pi, and the second part from pi to 2 pi. Similarly, this integral is also splitted from 0 to pi and from pi to 2 pi. Now in the second and fourth term, if we take theta 1 is equal to theta minus phi, in the second and fourth term, that is sine theta is equal to cos sine theta 1 is equal to sine theta into cos pi minus cos theta into sine pi. This is obviously equal to minus sine theta, and d theta is equal to d theta 1. So when we put this here, now you can see this detail and see that they add up to give us okay, this is what you get, and you can go through this page to see all the detail, and finally you get this result over here. So phi is equal to 2 pi 0 to pi j naught pr is equal to this. So you will have to go through the details of my notes to reach to this final result, that phi is equal to lambda over a into sine alpha j1 2 pi a over lambda into sine alpha. So that is the application of the integral representation, and taken as an example from the book by, let me show you this from the book as well. So the steps are also done here, and this is the Fraunhofer diffraction through the circular aperture. Here the example is 11.1.1 Fraunhofer diffraction, so you can go through these pages and then the detail of in my notes to reach to this result. Okay, so that's it about these topics which I wanted to cover today, and let me give you now some exercises from to solve few more problems from this exercise. Where is this exercise? If I can see. Okay, so these are the exercises. So I would suggest you to solve exercise 11.1.2, 11.1.6, 11. Okay, that's all. So you in our next lecture we will take up the orthogonality property of the Bessel's functions. Okay, thank you very much.